my voice is clear? My voice is clear. Yeah, please put a message on the group that class will start, and then let me share my screen. Is the screen is visible? Compound cylinder. We will discuss about compound cylinders. Okay. Total 27. So let's start the class. Okay. So till now we have discussed about your thin cylinder and thick cylinder. Today we'll discuss about compound cylinders. Okay. So basically, what is compound cylinders? It is the name suggests compound. So basically, your compound cylinder is a combination of two cylinders. Okay. So, when you work for thin cylinders or thick cylinders, if the internal pressure, suppose this is my cylinder, if the internal pressure P exceeds, it tries to burst out this cylinder. Okay. Sometimes it won't be able to carry this pressure. So generally what we do, there is a two solutions. Okay, we can solve this. We can suppose just assume that this is my cylinder and I have, let me draw in. Okay, I have free space here. Let me note. So suppose assume I have a cylinder of some radius. Okay, this is my cylinder and I have a pressure, I have a fluid here which is acting pressure on its walls, and it is trying to, and it is I'm annotating, it is visible, right? Annote is visible. So suppose assume this one is my cylinder of radius r, and this is the pressure acting on its walls. Okay, a pressure is acting on it, on the walls of the cylinder, and it is trying to burst out this cylinder. The internal pressure is so much high that it will burst out this cylinder. So what we can do, we can do to prevent that bursting force from the cylinder. What we can do, suppose assume this one is cylinder. Drawing is not bit good, just adjust. So assume that so this is my side view of the cylinder. Just assume that the internal pressure in the fluid is so much high that is trying to burst out. So we can prevent that bursting pressure. What There's one solution that we can this we can give we can apply some, we can wrap some steel wires. We can, if we wrap the steel wires, the pressure applied by this fluid will be it will be less. Just assume that you have a pen with you and you are wiring that pen with a steel wire. So this is one procedure to cope up the high internal pressure of the cylinder. Okay. The next is your compound cylinder. What you can do, suppose this is one cylinder. Okay, this is one cylinder. Again, you are inserting one cylinder. Uh, this is one. This is the initial cylinder. This one is the initial cylinder, and you are inserting that cylinder. Suppose this is one cylinder. This is one cylinder you have. This is one cylinder you have. You are inserting one more cylinder onto the previous cylinder. So it is a combination of one or two. It is a combination of two cylinder. Earlier I was having. Let me denote with. Let me denote once again. Change cylinder. So suppose this one was our one cylinder. This one was one cylinder. Compound cylinder, what we do, we insert one cylinder with another one, so that the pressure inside the pressure, it can resist the high pressure inside the fluid. Getting my point? What I'm saying, that there is already one cylinder you have. Okay, this I'm showing from the top view. You already have one cylinder and the pressure inside so much high that it will burst out. So what I'm doing, I'm wrapping the same cylinder when with one more cylinder. Okay, so this was the first cylinder, and this is the second cylinder. You are wrapping one more cylinder on the surface of the outer cylinder, initial cylinder. So this is the compound cylinder. This compound cylinder are generally used when we need very high pressure fluid to pass very high pressure fluid. Then what will happen if the pressure fluid is get increased? This cylinder tries to burst out. So prevent that bursting force, what we do, we wrap the same cylinder the with one more cylinder, so that the bursting can be reduced. Okay, suppose this let me note once again with another color. Suppose this is one circle, or this is the one cylinder. Okay, it is inner radius and this is the outer radius of your cylinder. So this is one cylinder which has this is the inner radius is r1 and the outer radius is r2. Okay, so r1 is the inner radius and r2 is the outer radius of the cylinder. So you are again you are inserting one more cylinder on the first cylinder. So generally, why it is getting lost again and again. So this is one cylinder you have, which inner radius r1 and this is the outer radius. Okay, next you are inserting one more cylinder. Then you have to see that this is the inner radius of the outer cylinder and this is the outer radius of the cylinder. That means I want to say that this is your r3, this is your r3 and this is your r4, and this is your r1 and this is your r3. Getting my point? That the radius of this is r1, this is r2, this is my diagram is not good. I'm not liking it. Let me draw once again. Just suppose this one is one circle of radius r1, and so assume that this is one my initial cylinder with radius r1 and radius r2. Its inner radius is r1 and outer radius is your r2. Okay, and again I'm inserting a cylinder. I'm making a compound cylinder, so its inner radius will be less than r2. Its inner radius should be less than r2 comparison to r4. So this is R4, outer radius of the cylinder, and this is your R3. So for this is your R3. So for compound cylinder, your R3 should be less than your R2, so that you can heat up that. I want to say that diameter, internal diameter of the outer radius should be less than the outer diameter of the inner cylinder, so that you can heat that cylinder to get inserted over the inner cylinder. So, are getting my point? What kind of the compound cylinder? You will heat the outer diameter, and you will just insert it out the you will insert the cylinder over the internal diameter and internal radius. So this is the R3 should be always less than your R2, so that it can easily get inserted over the surface. So see. When a cylinder is subjected to internal pressure, there is significant variation in the hoop stress across the wall thickness. This implies that the material of the cylinder is not being used to maximum advantage. It is possible to obtain a more uniform hoop stress distribution by the process of sinking one cylinder onto the outside of another. That means you are sinking one cylinder to the another. Let me allow some students, they are outside. Okay. So what you are doing, you are sinking one cylinder in onto the other. So that is how a compound cylinder looks like. The inner diameter of the outer cylinder is made slightly smaller than the outer diameter of the inner cylinder. What I have discussed, that your inner diameter of the outer cylinder will be, that means your R3. Your R3 will be slightly smaller comparison to your R2. Assembly is generally achieved by heating the outer cylinder until it can freely slide over the inner cylinder. On cooling, the outer cylinder will contract, and the inner cylinder is thus brought into a state of compression, and the outer cylinder is conversely brought into a state of tension. So suppose, see this figure. Uh, See now, this is the radius of inner, this is the radius of this is the compound cylinder. Okay, so earlier you have four radius, one, two, let me remove this. Earlier you had four radius, right? One, two, three, and four. So now you will have only three radius. How? The R1, this R2 and R3 will it will come in contact, and it will make a junction, right? This R2 and R3 will come in contact. When you sink out one over another, it will come in contact, and it will give rise to a junction. Okay, and it will give a single radius, and this will be the outer radius. So earlier you had R1, R2, R3 and R4, right? Now R2 and R3 get immersed into one single R. C, you can represent it by RC, that is the radius at the junction. Okay. So this is if this compound cylinder is subjected to an internal pressure. Okay, if this compound cylinder is subject to an internal pressure, the hoop stress will be the algebraic sum of those due to the internal pressure and due to shrinkage. So now the pressure applied by the fluid will be acted upon. Just assume that you have two member in your house. Okay, usually they will fight with each other. Suppose this is the one member inside cylinder, this is the outer cylinder. This will fight with each other, but when some external force applied on those two members, they will act as in unity, and they will cope up with the internal pressure. Okay, just assume that two brothers of a family. This one is the one brother, this one is another brother. Okay, this is the inside cylinder, this is the outside cylinder. So they will at first they will suppose at the starting phase I don't have any fluid inside the cylinder, so they will the pressure will act on its inner surface only, and here it outer surface only. Okay, but when I applied a fluid from outside, when I'm applying a fluid from the outside, they both are acting on this surface. They will act as a unity. They will made a contact surface. They will this will be the junction, and they will try to cope up with the stress. So if this compound is if this compound cylinder is subjected to an internal pressure, the hoop stress will be the algebraic sum of those due to internal pressure and those due to the shrinkage. There will be some shrinkage, okay, when you insert one cylinder to the another. So this yields a much smaller variation in hoop stress. So this is the internal pressure. Okay, this is the internal pressure acting on the cylinder. This is the shrinkage only, and now this is the combination of internal pressure plus shrinkage. Okay, so when you don't have fluid, there will be only one internal pressure. Means you can divide this condition into three parts. Okay, first the internal pressure only, second internal pressure shrinkage pressure is only at the junction, and then you can have the combination of these two. So, assuming that both cylinders are manufactured from the same material, okay, we are assuming that the both material, cylinder 1 and cylinder 2, or inner or outer cylinder, is made up of some same material, and the method of solution can be broken down into three separate effects. So we can analyze the cylinder into three parts. Number one, shrinkage pressure on the inner cylinder only. So at first the pressure is acting on only on the inner surface, then it is acting on only the outer surface, and then internal pressure on the whole compound cylinder. So just assume this is a condition of no fluid. When the fluid, just as you can also divide this into two sections. Here no fluid, no fluid is inside the cylinder, so they are acting sorry so they are acting independently. Inner cylinder is acting independently, outer cylinder is acting independently when there is no fluid, and this is the condition of fluid. So both are acting as unity. So see, 1 2 3, this is the junction radius, this is the internal radius, this is the outer radius, and in this condition, this is the internal radius, ry and ri is the internal radius, this is the outer radius, or you can say junction radius, and the pressure is acting from the outer radius. So for each of the resulting loading conditions, there are two known values of the radial stress, which is sufficient to determine the assumed associated Lame constant. So from last class, we derived some Lame constant, right? We derived some Lame constant. Anyone remember? For the hoop stress, sigma r and sigma c, we derived two Lame constants. Anyone remember? I've shared some PPT also. We came across two derivations, right? So this two was the conditions. Are you able to see the conditions for the radial? And I have changed to next screen. It is visible. My screen is visible. Please respond. I have changed to next screen. Okay. So these two are the basically these two are basically your we derived this from Lame's theorem. In the thick cylinders, we derived these two constants for the this is the radial stress, this is the hoop stress. So b minus r square minus a. So these a and b nothing but some constant value you have to find out from these two expressions. Okay. So we'll apply these conditions, 1 2 and this three condition. We have to apply these three condition over this Lame's equation. Okay, b by r square minus a, b by r square plus a. So first condition we have for this cylinder. So first condition for this cylinder, here your r is your ri, this internal diameter. So at internal diameter, as there is no fluid, so there will be no Students are still coming. Let me allow them. Okay. So when there is no fluid, there will be no radial stress, right? So this is 0. So this is one boundary condition at this surface. Okay, at this surface. Next, at r equals, when r becomes rc, that is the diameter. That is rc is your junction radius. So when r is equal to rc, at this surface you are getting pressure from the outer that junction. Okay, the junction here it is getting. This will be your junction point. This will apply some pressure on the inner surface, means just general pressure, not because of the fluid, the general pressure, and it will be in compression nature, so they have considered minus p. So you have to use these conditions in the Lam's theorem, so, to find out a and b. Okay, so this is the condition when you don't have fluid and for your internal cylinder. Next condition you have. Here they have mentioned where RC is the interface radius. The stress is compressive since it tends to reduce wall thickness. It is in compressive nature because it tends to reduce the wall thickness. Next condition we have this one. So when your R is equal to R naught, that means your outer, this one. Again there is no fluid, so there will be no radial stress. So R sigma R is your 0. Next, when R is RC, for the outer rate, for the see, this was the inner radius, right? This was the inner cylinder, so RC was this one. Now for the outer radius, this RC will be your inner radius, and you will have one more R naught. Getting my point? This was your inner cylinder, so it has its internal diameter, and outer diameter will be its junction point. So that's why RC is shown this one. But for the outer cylinder, RC will be like its inner radius, and R naught will be outer radius. So at R naught, you don't have any fluid, so you don't have any radial pressure on the surface. So your R naught is your R naught your R naught is 0. But at this RC, at the junction, you have this pressure, right? This P. That's why minus P. Clear? So we have completed with two conditions when the fluid, there is no fluid, for the inner cylinder and outer cylinder. Next, internal pressure only on the compound cylinder. So because of the fluid, will have these conditions. So your R will be R naught and RC. That means there will be a outer radius and a junction radius. So at outer radius, on the outer surface, there will be no pressure, only inside pressure. When you have the fluid, this outer surface doesn't have any radial force, because from outer direction you are not getting any pressure. But the outer surface of the inner radius, you are getting a pressure of Ti. So this is the condition. So these three are the basic condition. You have to apply this condition on this Lam's expression, which is B for radial B minus R square minus A, and for hoop stress B minus R square plus A. You have to put these conditions to find out the various A and B for these conditions. Okay. So therefore, for each condition, the hoop and radial stress at any radius can be evaluated. This means that the various stress can be added us to compute the stresses in a compound cylinder subject to both shrinkage and internal pressure. So they are saying that by using these conditions, you can use Lam's expression to find out the various radial and hoop stress. So there is one more thing, shrinkage. So when we design a compound cylinder, we need to relate the difference in diameter of the mating cylinders to the resultant stress. So what is the so this shrinkage? So see the figure. This is the original outer diameter of inner cylinder. Original outer diameter. This was the inner cylinder. This is the diameter of the inner cylinder, which is outer diameter, and this is the I said na there will be a contact radius. This was the, like, let me draw once again. As I discussed that earlier, what we had 4 radius, right? We had some, okay. So as I discussed, we had 4 R4 radius. This one was our initial cylinder with having R1 and R2, right? Then we inserted one more cylinder with radius R3 and R4. We have inserted. Now this R4 and R1 will be independent. This green and blue, that means R3 and R4 will have a common radius. That is, it will have a common radius. That my pen is. Let me draw once again. So this was the R1. This red one is R2. This green is R3. This green is R4. So when we join these two cylinder, we'll get a final radius. That means this R2 and R3 will combine to make a new radius. It will combine to make a new radius, which you can say contact radius, and this is the final radius. So there will be shrinkage in the materials. Okay, outer radius will try to shrink the inner radius, and inner radius will try to expand. So inner cylinder is in compression and outer cylinder is in tension. It tries to close the cylinder, and the inner cylinder will try to expand. So there will be some shrinkage. Okay. So when we design a compound cylinder, we need to relate the difference in diameter of the mating cylinder to the resultant stress. The difference in diameter at the mating surface is called the shrinkage or interference. So there is an interference. So see, this is the R3 this is the R2 I was talking about, and this is this dotted line is R3 I was talking about, and this dotted line, this one, this is your final common radius. Okay, so there is a shrinkage pressure acting on this surface. So you need to consider that also. So let us consider the compound cylinder shown below. The materials of the two cylinders are not necessarily the same. So the material of the two cylinders does not need to be of same material. So that means they are saying कि it does not necessary to be homogeneous in nature. So P, pressure set up at junction of the cylinders due to fit. So these are the notations given, what they have assumed. Sigma theta I is the hoop stress on inner cylinder at junction, and hoop stress and sigma theta naught is your hoop stress on the outer cylinder. As I discussed, one will be in compressive nature, one will be in tensile nature. And these are the radial shift of outer and radial shift of inner. Since the circumferential strain is equal to the diametral strain, so you have the since the circumferential strain is equal to the diametral strain, so we have seen earlier that circumferential strain is represented by E theta and diametral strain is E theta. So your circumferential and diametral strain is equal. In compound cylinder, both the values are equal. So circumferential strain at radius outer, so find out the radius. So this will be the circumferential stress at the junction at the outer cylinder. This will be at the inner cylinder. At inner cylinder it is E theta I, at outer cylinder it is E theta naught. So shrinkage is your del naught plus del I. Put the value of these two, will get an expression. And your total shrinkage or interference is given by this value. Go through the derivation. Generally, both cylinders are of when the both cylinders are of similar matter, so your E1 and E2 will be same, replaced by E, and your V1 and V2 is replaced by simple V. So this formula will becomes to this one. Okay. Generally, if the material is different, your formula will become this one. If the material is same, this E1 and E will replace the E. This V1 and mu1 and mu2 is replaced by mu, and this formula will reduce to this one. So you have to remember this one. This formula is also this formula is also. Okay. Go through the derivation. So one example is also given to you. They are asking a compound cylinder is formed by shrinking a tube of 250 inside diameter and 300 outside diameter onto so that various diameters is given to you. They have asked to find out if the compound cylinder is then subjected to an internal pressure of 8 MPa, calculate the hoop stress distribution. So use the conditions. Okay, at R, these are the conditions. By using the conditions, we have put the values in the Lehm's equations and we have found out the value of A and B. Right. After finding A and B, you can find the sigma theta, that is hoop stress, or sigma R. So this is the conditions for inner tube. This was the conditions for outer tube. This was the conditions for inner tube, and this was the condition, third condition. So using both every condition they have found out the A and B and put the value in the Lehm's equation to find out the theta, hoop stress and radial stress. So go through this numerical. This part is not required. I'll share this PDF. So till this numerical, go through once. Okay, I'll share right now. So till this numerical, that means till page number 7, study. Okay, go through. If you have any doubt, please ask me. So basically this part is over, and then we have stability of dams. We'll discuss that part. Stability of dams, retaining walls. We'll discuss that part in your next chapters. It will come under next chapters, not in this chapters. Okay, because there are some theories related, so we'll discuss that in next chapters. Stability of dams, retaining walls. So we're done with first chapter. We have discussed. Go through the PPTs, make notes, go through the recording links, or just make notes either from my notes. If you find better notes, you can do that. But study and clear your concept now. If you don't understand, text me. Okay, text me or mail me your doubts. So what are the topics we have discussed? Why you are writing Jojo, ma'am? Why you are writing your roll numbers? I didn't ask your roll numbers. Why you are writing your roll numbers? So tell me, what are the topics we have discussed so far in this chapter 1 or module 1? What are the topics we have discussed? What are the things, what are the theories we have discussed over the whole chapter from day 1? 50 students are present. You are from section A, no issue. Thin cylinder, yes. And thin thick cylinder, okay. Compound cylinder, good. And only these 3. Are you making notes or not? See, clear your notes, clear your doubts from this semester only. If you are thinking of applying for GATE exam. Okay. Now third year students also can apply for GATE exams. Some of you might be appearing for GATE exams. So clear those. In fifth semester you have very important subject, and it is the foundation of civil engineering. All the subjects you have, all are the foundations of civil engineering, and all the subjects are important from GATE point of view or your state exams. If you want to work if you want to work in a state government, so all the subjects are important. So clear your doubts from your teachers, from me now itself. Okay, बस थिन थिक सिलेंडर से पढ़ा और कुछ नहीं पढ़ा हम लोग ने. और forgot. What happened? 50 students are Febina. What happened? Not replying. Bamang, 57 roll number. What happened? Axial load, stresses in cylinders. And Guneshwar, Jinsan, Kishan. What happened? Risha, Likha. Are you there or just attending the class? Trust. Yes, good. Method of section, method of joint, good. And yes, something like stress strain diagram. Studied or not? Various properties from stress strain diagrams. Don't remember? Okay. Anyways, so from the next week, we'll start with module 2, and most probably in October you'll have your first session maybe. I'll let you know. So go through all the topics from the first chapter. Okay. Method of joints, method of sections, then this thick stress analysis of thick, thin, and compound cylinders, then stress strain diagrams, and the basics we have studied so far. Okay. So write your roll numbers in your chat box. Please write your roll numbers in your chat box. Done? Any questions? Anyone? Any questions you have?
No, ma'am.
No, ma'am. What about others? Any questions? Ma'am, it is gonna be helpful for me if I refer from those PDFs. Yes, yes, yes. You can refer from those PDF also. Not a big issue. You can refer. You can refer those PDFs from the ERP also. And what I'm giving in the groups also you can refer. You can refer from anywhere. Okay, no issue. You can refer from your some books. I've given some books also. List of books to someone asked me. I give some list of books to CR. I forgot the name, but I gave some list of books to them also. You can study from books also, and you can refer those PDFs also, and you can refer also the notes I have given. It's up to you. Okay, you can refer from anywhere. The concept will be same anywhere. Okay, the concept will be same. So I know there are issues from in the live classes, so not a big issue. You can refer. Any more? Anything? Anything? So this is the chance you want to say something. So say if you have any issue regarding the subject, regarding the topic. No one. Hope there is no issue. We are good going then. Okay. Any issue? 50 students are there. Make notes, okay? I'm telling repeatedly, make notes and study. See, daily we are learning small topics. Okay, go through the derivations. Uh, some students ask me the simple things about integration. So if you won't go through the integration derivation fully, you won't understand the integration part. So everything is related. Okay, and many one of you not submitted me the assignment. So see, take assignment as important. See, this will till now I don't know what will happen to at the end of means how this. I think this semester will go virtually because cases are increasing here. I don't know when it will open. I really don't know anything. But so take attendance, take presence in the class, take this your replies in your chat box plus your assignments very seriously. Submit it very seriously. Attend all the class very seriously because all the marks will given based on that. Okay, I'm reminding, repeating from again. Last class also many good students didn't attend some classes, and because of that they got very less marks in there. And we have given marks, but the examinations department just set the some formula, and you got the results from that. Okay, I'm telling this openly. So do your best from now itself. Okay, attend class, submit the assignment on time. That's it. Any